Hello everyone. So today we'll continue in this video the CTQ number 9. In this question actually six circuits were given. Out of these six I am taking four here in the part 1 and next part I'll take as 2. So the question here was to calculate the gains and the voltage swing at the output. So first thing that we have to see what are the common aspects of these all circuits. So, in general, I should say these all are the inverters, or I can say these are the directly looking the voltage amplifiers, or can say common source amplifiers. So, we will get different gains, different swings depending on that what kind of loads we are using here. So, the point here is that one common thing that we can see is NMOS amplifier or NMOS transistor, which is taking the input and giving the output at its drain. Rest means all four circuits are same because of that point of view that all are taking inputs at the gate of NMOS, source is connected to ground and output is a drain. The only thing is different is the load. Here the load is RD, here the load is ID, and here is a PMOS device with some external biasing BB. Here is a diode connected PMOS device. So we have to analyze that what is the behavior of a particular circuit, particular structure, depending on their load. So in general, what is happening here? I can draw a general structure where this is a load and it is a common source amplifier. It is known as common source amplifier. In general, what you do, if this is the input, this is the output, and it is some load Z, it is my VD. And in general, for the common source, we know what is the gain, and my V out is think what minus GM RDS times Vn. This is the general expression we know. And what is the RDS? This RDS is the RDS of this transistor, and also I should write the RDS parallel Z. Yeah, RDS parallel with Z is the impedance. This is the output voltage. This is on any in general common source amplifier. Now we have to analyze these circuits one by one. So one concept that I will tell you what is happening. This is the important thing. Actually, the current source or the resistor or whatever the active PMOS device, what they are doing, they are acting as a voltage source or their current source. So we have to see this thing. So what is this? My lower transistor. This is my lower transistor, which is V in one source. Let I'm taking this transistor, and what we are seeing here, we are giving an input at gate and we are sweeping it. Source is grounded, so what should be there? The current should change. This current should change. Current is the function of input voltage, so I can say it is what, it is a voltage controlled current source. So I can say it is something like a current source which is a controlled by a gate voltage, so it is a voltage controlled current source. Now what is happening there on the top, let this is my one another current source. Let's say this is my another current source. I am picking the second circuit as of now. Let me tell you the concept, then you will understand. So what is happening here, it is the again current source. It is a independent but is a current source, so we are connecting both. So what is happening in general, we are connecting two current sources in series and we are asking about this voltage, middle voltage. So this current source is your ID, which is an independent current source. It has its own value, and this is the voltage control current source. So what ideally we know? We know that let I say this as a I X, then what will happen? Two current sources in series means ID should always equal to IX. Did we are agreeing that? So this is the basic functionality. So where this V out will land is depending on the condition, then these two currents should be same and accordingly V out will adjust itself. So I should start with the same concept of the second circuit and I'll explain how the resistive load and the active PMOS devices are behaving here. Okay, so okay, so what the concept I was explaining here, the concept was there are two current sources in series. One is my ID and one is my IX, which is depending on the voltage. It is depending on the voltage. It is I call voltage controlled current source. So where this mid value lie, it is a question, and the value or the range of input or will decide where this Vout lie. So I am just telling two things. First, I'll draw the characteristic of current, this IX current, which is nothing but a current of NMOS, which is nothing but a drain current of NMOS. I'll draw one thing, and this is my IX, and here the input. So what is happening in general? I want to know its drain to source voltage. So what parameters I will write for this transistor, lower transistor? I will write VGS. VGS is my V in. I will write VDS. VDS is my V out. And what is the ID? This is my IX I am considering here. Okay. So these are the parameters. So now we will see from the characteristic point of view. Okay. So this is my ID for any NMOS, and I am sweeping or I am wearing my VDS. Okay. So what is the effect on the current? We will see. This current is something like this. Okay. If these are not that accurate, but you can understand what is happening here. So what are these curves? These are the curves of current for different values of VGS. Let's say this is my VGS1, this is my VGS2, VGS3, VGS4. Okay, so this way my VGS is increasing. It means my input is increasing. So if I take a particular means point on the voltage VDS, then what I can say, if I am taking this VDS, my VDS is nothing but V out, and if I am saying my VDS or output voltage is constant somewhere here, that I call, let's say, V out prime. It is constant at this. It means with different input my current is changing. Okay, it means with the different inputs my current is changing. But what you can see here, this is a constant current. It is a constant current. So this upper source is forcing a constant current, and lower source is changing with input voltage for a particular output. So what I can say, that my output that I am fixing constant. So with the varying in the input like different VGS, my current is changing. So this situation is not going to happen because you are pumping a constant current from the top. So what is going to happen? Now just elaborate it. If I am changing my input, again I'll draw. So now we'll draw a new curve. So this is the ID. Again I'll draw VDS, which is my output, V out. Okay. I'll draw a few closure curves here because I want to tell something. Okay. Okay. Yeah. So these are for increasing VGS, or I would say increasing input. Okay. So what I want to tell you here, now I am pumping a constant current from the output. So I'll draw it here. This I'll call it I, let us say I out. I'll call it I out. If it is written ID in the back page, I am just modifying it to I naught. So it is a constant. So what you can see for the different values of like VDS, where your current will lie, or where your output voltage will lie. So I can see from this that for particular VDS, if I'm saying this is my VGS1, sorry, VGS2, this is my VGS3, and this is my VGS4. This is the VGS1. So what we can see here, my curves are cutting, here my curves are cutting, and here my curves are cutting. So from here, if we trace them on the x-axis, we'll see that for a particular value of VGS, increasing VGS, my VDS is reducing. Means suppose here was my VDS1, here my VDS2, here is VDS3. Okay. So what thing we can see? Let's with this is a limit VDD. So this curve for the VGS, lower VGS, this curve is if I'm extending it, it is not cutting this red curve, or it is cutting after VDD. So what we can conclude from here, this curve I should retrace. If I'm extending this curve, so these are cutting somewhere here, beyond VDD. So what we can say? Is it possible that my output node will set at voltage beyond VDD? No. This voltage is obviously greater than VDD where my current and voltages are cutting. So what we can see, when our gate to source voltage is such that our current is the current generated in the device. Okay, that point I'll mention. If my gate to source voltage, that I call VGS, is such that current generated by the device, which is my NMOS or the source device, by the device is, so if my gate to source voltage VGS, gate to source voltage VGS is such that current generated by the device is smaller than the current pumped, smaller than the current pumped, which is my I naught, then what will happen? My VDS or Vout will try to reach VDD only, because it cannot go beyond that, or it will reach VDD. I should not try, but it will reach VDD, because we are seeing that the cutting point of this I naught and this characteristic for the VGS1 is coming after the VDD, but it is not possible. Okay, because your any node cannot go beyond this VDD. Okay, so what we can see, when this current Ix is lesser than this I naught, then you can say your Vout node is landing at VD. So this thing now I can explain in this way. So what we are seeing here, for the different VDD, sorry, for the different VGS, means you are increasing the input, then output is decreasing. Okay, output movement is this way. This is my output movement, and this is my input movement. So when I am increasing my input, my output is decreasing. So this is the general nature of my inverter. What we can conclude from here, this is the current source what I am pumping I naught, and this is my transistor. Okay, and if I am sweeping the input from 0 to VDD, so if my input is lesser than the VT, means when the current is 0, I can say ideally. So when I will say my Vin is less than VTHN, what will happen then? Ix, which is the current across this transistor, Mn is 0. Ideally, it is 0. Okay. So what should be happen? But we are pumping some current from the top. So what will be happening here? This point will hit your VDD, or it will try to go beyond VDD but cannot go. So it will hit the VDD. And when my Vin is equal to VTHN, or I'll say the Ix is not equal to 0 but small, So in that case also I'll say my Vout is near VDD. Okay. So when the current will start, or I'll say this I naught is also very small. Let I say this is also small. Okay. So that my current generator Ix is coming in this range. Then I'll say some voltage Vout will start developing, which is less than VDD. Okay. So what we can see in general for this. So this is my V out, this is my V in. You can see here till this point somewhere here, let's say VTH, it is the VDD, and after that it will try to reduce, and now the point comes, what point it will hit. Will it hit the ground or will it not hit the ground? So that we have to see. Okay, so now I am pumping a constant current, that is sure, and this voltage V in is reached VDD. Okay, out. So as we are increasing this V in, so I'll say this current should increase. This current should increase. Ix should increase. So from the characteristic, what you can see, let's say for this VDD, so this is something like this. Okay, this is for V in equal to VDD, VDS, ID, and here somewhere here my I naught. Okay, so you can see here it will cut near the origin. It will cut my VDS line, this which is my output, near the origin. So it is nearly 0 volt. What I can say here, so it is trying to reach near, what is say, near to origin, means the current is trying to be 0. But actually what we are means pumping, like I am pumping the I naught which is not equal to 0. If even the I naught is very small, from the characteristic we can see, even if my I naught is very small, suppose it is here, whatever current I am pumping here, it is very small, let's say, even it is cutting at some point which is near to the 0, but it no, V out is not exactly 0, so it is supporting that value. So what I can say, in this case my V out is very less. So V out is very less means VDS is very less, so VDS is small. Okay, so what you can say here, my VGS, which is nothing but equal to V in equal to VDD, is large. Let's consider VTH as 0.5 volt, and what you can see, and VDD equal to 3.3 volt. What you can say, what is my overdrive voltage? Overdrive is VGS minus VTH, which is coming at 2.8 volt, and it is very much greater than your VDS. Let's say VDS equal to V out is nearly 0, which is my 0.1 volt. Okay, so what I can see here, in linear region, when my transistor reach in linear region, it can be replaced by some resistance, which is my R on, and R on is what, 1 upon mu n COX WIL VGS minus VTH. Okay, so what is the minimum R on? Minimum R on is nothing but when my input is reached VDD. Okay, so when my input is reached VDD, the R on is minimum, because this particular voltage reached VDD, then my R on is minimum. This is called R on min. So what I can say about the circuit, I can say I am pumping a current which is I naught. It is whether smaller or larger, I don't care, but my transistor is in linear. So what I can say, I replace this as a current source. Sorry, this as a resistor. This is my R on. So this V out will set at the point. So V out is what, I naught times R on. Okay, so it is not exactly 0. It is some value which is supporting this current. So this is my I naught R on. Okay, so this is the characteristic for this particular question. Okay, so now instead of I naught, if we are using the resistor, then what will happen? So if we are using resistor VDD, which is my 3.3 volt in my case, this is my RD. Okay, so in this case the conflict is not here. What was the conflict? Conflict was two current sources in series. Okay, so previously what was here? There were two current sources. This was my I naught, which I previously called ID, but it is I naught, and this was my IX. and this was the voltage we have to check, and this was my voltage controlled current source. Okay, but in this case it is not like that. In this case, what is happening, this is still my voltage controlled current source, which I call Ix, but upper device is nothing but a resistor. And what is resistor? Resistor can behave as a both. If I am applying some current to it, then it is a current controlled voltage source. If I am applying a current across it, then this voltage is well defined because there is a no conflict. Resistor can act as a current control voltage source and voltage current source. If I am pumping a current Ix, then I can say this V out is nothing but VDD minus RD Ix. Okay. What about the Ix? Ix is nothing but controlled by gate voltage. So it is a voltage controlled current source. So what you will see here now exactly if I go inside it. So again try to look at the characteristics first, then we will see where we are lying actually. There is no problem. So what should be the current here, that I call again I naught, and what should be the current here, what I call Ix. But whatever I am writing here I naught is not independent, it is dependent on the output. So there is a no conflict as well. So what I will write here, I naught is Ix is again dependent on your input voltage, the function of input voltage that depend on whatever the linear region or saturation region, we'll write that equation accordingly. But I want to know, again I will write two things. What is my VGS? This is my Vin. What is my VDS? It is my Vout. What is my ID or IDS? It is my Ix. So I want to plot the characteristic again. This is my VDS. This is my ID called Ix. Okay. So I want to change this VGS again. I want to plot this. So these are four plots for different V in. That I will say V in is increasing. Okay. So these are for Ix. Now I want other thing. I want the equation of I naught also. So I naught is what? I naught is nothing but I can write in terms of V out like minus V out by RD plus VDD by RD. Okay, so it can be written as like it is something at a slope of minus 1 by RD. So I can write at V out equal to 0. What is this? This is my VDD by RD. So I am again plotting the current curve. Okay, and at I not equal to 0, what is this? This is the point where V out is equal to VDD. Okay, so I am again plotting this curve. So this is also the plot of I naught. This is also the plot of current. So the two current sources in series, but this time there is a no conflict because the upper current that I am calling R no I naught is dependent on the output itself. So from this characteristic, I can write or I can find what are the cutting points. Okay, what are the cutting points? What you can see, these are the cutting points. These cutting points are again telling me that if I'm increasing the input, my V out which was coming here, now it is reducing. But what extra thing that we can see from here, and when there was a constant current source, we can see with the increase in input, there is a slightly smaller change in the output. Okay, because there is some, let I say V out or sorry V1, and that I'll call V out 2 3 4. Okay, so here we will see for a wider change in the input, this much change in the input range, we are getting this much change in the output range. So from here what we can see, this gain is less, gain is less. This thing I'll again cover, but from the DC point of view, what we are seeing that if I'm increasing the input, my output is reducing. So for particular value of input, when this there is no current, then I'll say both the characteristics are cutting and VDD only. So maximum value of the output is VDD, and for some higher inputs when there is a no current, or I'll say when there is a VDD is VGS is much higher, or it is near to this origin, then I will say this point will land somewhere at 0. I can say like this. Okay, when my input is VDD, I will say that the minimum Vout is nothing but a 0 only. Okay, so I can write this thing. So what is this? Because now RD is deciding my output depending on the current flowing through it. Okay, and current is decided by this input transistor. So I can say this Vout is nothing but this. I will say ID, which I call IX here, is nothing but VDD minus RD IX. Okay, so IX can be 0, means VDD can be, oh sorry, Vout can be VDD. Yeah. So what is this? When this is I call VTH. So here my VDD, and after that it is reducing and it can reach 0 because it need not to support any current. Okay, this is my V in, this is my V out. So it can reach 0. It need not to support any current. Okay, this RD is not creating its own current. Okay, so in previous, in case of current source, this value was not means 0. It was something which was nothing but R0 times I. Okay, R1 times I. So what you can see here, yeah, gain from these two points, gain from characteristic point of view. So I think it was not clear for all. I'll take this point again. So if there is a constant current source, then what was happening here? This was my PDS, also I call V out, and I was plotting, let's say, three characteristics. This is my IDS, and a constant current source was here. I'll compare two lines here. This was my constant current source, I naught, and this is my RDS. When my RD is there, then this was the characteristic. Okay, something like this. So what you can see, what are the cutting points here? What are the cutting points here? So this is nothing but a variation in output that I'll call del V out. For how much del V in? This much del V in. Now for the same range of del V in, we'll see the del V out for this particular. It's cutting somewhere here. Okay, at this point. What I want to conclude here, because the current is constant, so this constant current source is providing the infinite impedance, means directly we can see from the expression of the gain, also you can see from the characteristic that for the similar change in input, this much output we have, this much output change we have. Okay, because the characteristic is so flat for this ideal current source, characteristic so flat that for a very close means these current characteristic for different VGS, this is my nothing but increasing V in, this output is changing so much. This thing we also know for the constant current source, what is the expression of gain? It is nothing but output is nothing but minus gm rds parallel r current source. Okay, which is vn. And for rd, what happens? This thing can be written as minus gm rds parallel rd, which is much smaller. So in general, this we can write simple GMRD times Vin. This thing is much higher than this. Okay, so this thing we can see from the expression that we have seen always. There's for a constant current source, there's an infinite impedance, or there's a very large impedance for a current source, but RD is there is smaller resistance, so gain is large. That we can see from graphical point of view, graph point of view also, or say from characteristics also. Okay, so the rest thing was this current source. The current, again there is a current source which I call PMOS. Again a current source which is biased externally, BDD. This is my third circuit. and this is my input we are varying, output we are plotting. So what will happen for this? Again there is a conflict. We are providing some current through this current source, which is also voltage control current source. This is also voltage control current source, and but its voltage is provided externally and it is fixed. So some I naught is generated here, and it is also current source, which is again voltage control current source, which we are controlling through input, and input is varying from 0 to VDD. So what will happen again? If this means PMOS, which are externally biasing, has some finite output impedance, then what you'll see, this instead of this flat characteristic of I naught, you will see slight change in the slope. Okay, so gain will be little lesser than that. I will plot here only. Suppose I'm getting this kind of characteristic. So this is for this my voltage controlled current source PMOS device. This third circuit I'm talking about. So gain is little less. So these are my cutting points. Okay. So in this case, gain is greater than the case of RD, but slightly less than that. The case of okay, yeah, slightly less than the case of ideal current source. Okay, I'll use my black pen. So yeah, the gain is still this you can see. Change in output voltage is much higher. This slope is coming due to this means there is some resistance associated with this current source, which is called IDSP. Okay, due to this associated resistor, we can see this current source has not direct straight. Instead of it has some slope. Okay, so this current source has some slope. This is my V out, which I also called VDS, and this is my IDS. Okay, so this is the for current source, which is my PMOS current source. Okay, so due to the slope, the gain is less than this ideal current source case. You can analyze it in more detail. Again, you can see this output can go what it can go maximum, because you are forcing some current from the outside or from the top side. So your output will hit VDD when there is this V in is lesser than VTH, and when this will start conducting, it will try to reduce and the output will start reducing, and after that, because we are forcing a constant current through due to this bias voltage, this is nothing but external bias. I'll talk a little bit about this also. So what we are doing here, actually we are making the VGS constant. What we are doing, we are making VGS constant for this PMOS, and if VGS is constant, I'm generating a constant current source. I'm generating a constant current. Okay, so by biasing some in some saturation region externally, we are just generating a current source. So there's no difference in this ideal current source and this current source structure analysis, because there's only introduction of RDSP, which is a finite impedance of the current source, which is also higher. So there will be some slope in this IDS-VD curve. So what we can see, instead of zero slope, it has some finite slope. Okay, so it will contribute to gain higher than this is the case of RD, but lesser than the case of ideal current source. Okay, so for the third circuit, gain is higher than the case of RD, but lesser than the case of ideal current source. Okay, now last circuit left is my PMOS diode connected device. So what we are knowing about this device? It is again a means voltage control voltage source. Sorry, current control voltage source. Okay. So what we are seeing here, I am giving an input, varying input, and this is my output. What we are doing here, I'll change the pen. Okay. So what we are doing here, we are generating a current, which I will call Ix. It is nothing but function of V in. I am generating a current, and this current is passing through this. So we are developing a VSG voltage here. What I can say, VGS magnitude or VSG we are generating, because this device is always in means saturation, because it's a diode connected device. What we know this current. 2 Ix mu P Cox WIL of P plus VTH of P. So this is the VGS voltage we are developing, and this voltage is depending on this current Ix. Okay, that's why it is called current controlled voltage source. So it is also not creating any problem because this is also against the this conflict. It is not creating this conflict. Two current sources in series. Rather, it is creating well favorable condition that we are generating some current here Ix, which is nothing but a voltage controlled current source, which is the function of input voltage. Okay, so we are generating this voltage and we are deciding this current, not current. We are not a current source. We are deciding that voltage. Okay, so what you can see, what is my output voltage? The important thing for us is the expression of output voltage and the swing. Okay, so what is my output voltage? My output is nothing but it is VDD minus VSG. Okay, so this is nothing but depending on again current, because the VDD minus VSG is again the function of my Ix, which is nothing but a function of input. So I can say VDD minus function of input. Okay, so output is the function of input again. So what you're seeing here, if I'm generating a current, this thing I already explained in great detail, in particular I think CTQ maybe, or not in CTQ, then in the 5 transistor OTS series, but I have explained all the circuit well. Actually I'm talking it about more here. Let my Vin is less than VTH. So first I should note these three things. Always try to note these three things. What is your VGS? My VGS is here, is Vin. What is my VDS? My VDS is V out. And what is my IDS, which I can say ID or IX. Okay, these are the three things. Okay, so when my Vin is less than VT, what I will say, ideally for NMOS should not have any current. This is the point. If it is not having any current and my the upper transistor is means what I will say, and this is in diode connected fashion. Okay, so I'll say what is my upper transistor. My upper transistor in diode connected fashion. So I am saying that the current going here is 0 amps. Okay, and here it is well connected. It is in form of the diode connected form, so it can be in saturation. But what is happening? The current is not flowing here. I can say this VSG. This VSG can be also less than or equal to, this VSG can also be less than or equal to VTHP. Okay. So there is also concept of sub-threshold conduction that I am not talking about it from the point of interview. It is not that important. Sub-threshold conduction. Conduction. So not important that much from the point of view, not that important for interview. If someone is showing the interest, then you can mention that due to the sub-threshold conduction, this current is not exactly equal, or I'll say it will start or it will remain conducting till the point when this VGS is somehow lesser than the VTHP also. In that case, my Vout will reach somewhere higher. So my Vout is ideally for the zero VT, it should be, sorry, for the zero current, it should be VDD minus VSG, where VSG is nearly equal to VTHP. So from point of view of drawing the characteristic, you can write this. Okay. So when my input was less than the VT, I am just considering, and there is no current. There is no current means my PMOS has this point VDD minus VTHP magnitude. Okay. So I write it again. I have given its proof in simulations also, but from the viewpoint of interview, it is enough. So this point will lie here, and after that, this will go, and you will see whether it is touching the ground or not. Okay, this is like that. But in general, what I will say, in practical case, due to the substitute conduction, this point will hit somewhere near to this VDD. This point is somewhere near to the VDD. Okay, so I'll say this is slightly less than del only. So this difference coming due to sub-threshold conduction. You can read this concept more, or you can see my other CTQ where I have explained it well. Okay, so what is this point? Will this means output reach zero or not? That we have to see. Okay, so let this is my device PMOS, and it is in diode connector fashion. Let my V in hit VDD. So happen? What will happen at this point? Again, I'll explain the same thing. Then this V out is going down. Obviously, we are seeing from here. V out is going somewhere here down. If V out is going down, let I am saying it is reaching point 1. I am quantifying it, and it is 3.3 volt. Because VDD is 3.3 volt. Okay. So what I can see here, let VTH is again 0.5. So what is V overdrive, which is nothing but VGS minus VTH. It is again 2.8 volt. So what is our VDS? VDS is much lesser than V overdrive, means triode. So again we can find this impedance. What is the impedance? That is a R on. This is 1 upon mu n COX WIL VGS minus VTH. So it is some minimum value because this is reached at 3.3 volt or VDD. So this is some finite value. Finite value. Okay. So we are in triode region, one thing, and we have some finite resistance. So what I can say, it means what is happening with this? There is sufficient VGS for this device because your Vout is near to means zero. So what I will see, you will see that what is happening for PMOS. For PMOS, your VSG is also enough, which is under 3.31.1 means 3.2 volt is also equal to VSD. So when both drain to source and gate to source voltage are enough for a device which is also in saturation, then it is pumping a current, it is forcing a current. It means this is still is in saturation and has enough current also. So it is forcing current that I will call I naught, and that I naught is nothing but you can calculate from mu p cox by 2 because your device in saturation times overdrive square, that you can calculate. So this current is still is forcing, means this node cannot reach zero because your lower device in linear region which is R on. So your V out has some value which is nothing but from here we can see my V out min has some value which is R on times is I naught. So it will not hit the ground. It will not hit the ground exactly. If it hits the ground, then what you can say? If it hits the ground, it will say that the what should be the ix? Ix should in linear region what should be? V out by R on. Hit the ground means this R on is too small, then Ix is too high, or I can say infinite. It is not possible because you are forcing I naught which is fixed from the top. So my device has to support that current only because in that case two current sources are coming in series. In other word, I can say in other way. Rather, it is not a current source. That upper current transistor's VGS is also depending on what current we are generating from the lower device. Just I am saying this the top there is a current source. Let's say which is a magnitude I naught, which is in saturation device in saturation. So it has some current, and to support that current, our lower device should also sink it. Okay, so it is syncing with the magnitude of R on. So we can say the voltage minimum is a V I naught times R on. Okay, so this is not exactly a zero. I'll say it is some R on times I naught. What will be the I naught at that time from the PMOS? So I think I have explained from the gain point of view. Also, you can see. I think for this I have not drawn this characteristic, but you can see you can draw by its own. So for 3 I have explained with the characteristic, and also I can take the characteristic of this also. So what will happen? Let I say in different way. What we know from the small circuit point of view, small signal point of view, it offers a gain like my V out is what? Because looking at impedance is GM of this upper transistor. What I will say minus GM of my N divided by gm of p times p in. So gain is small. I'll say gain is small. If 1 upon gmp is of order of rd, then I can say these two devices, these two structures are giving me the same gain. Okay, and from a swing point of view also you can see. Okay, so from the gain point of view these two structures are same, but from the swing point of view it is giving me more swing because you are getting output max is VDD and output min which is ground 0. This is giving me more swing, but what it is giving me, it is giving me maximum as a VDD minus VTHP. And what is the minimum? Minimum also nearly 0 I can say, but it is somehow R on time some I naught, nearly 0. So I can say swing is less. Swing is less for diode connected device. There are other advantages also, but rather you can say this circuit has the advantage because it also is only means it is following Ohm's law. So because of it's following Ohm's law, this voltage is directly you can say dependent on what is a drop across this RD. So higher the currents, if you need some higher currents, then there is a more drop. For higher current, there is a more drop. Okay. In DC condition, if I am saying, let me see this structure. If this output is let's say VDD by 2 in DC case, then what is the current here and what is the drop here? You will see here drop is not that much. What is the drop? Drop is nothing but BSG, which is depending on what? This is nothing but depending on this current equation in saturation. What is the current equation that you can write? This is that voltage. Okay, and what is the current here? Let's say this is also your VDD by 2 means okay that I'll say is also VDD by 2. So what is the current here? Here current is VDD by 2 by RD. So I can say VDD by 2 RD. This is the DC current. Okay, and here the current is what you can calculate from here. Okay, so instead of writing this, I should write what is my VSG. VSG is VDD by 2. So we can calculate the current. Okay, and this drop also can be calculated. Here we can say due to this RD, power loss is there. Power loss is there. So there are also other disadvantages you can see by your own. There are some things that I have covered here, but you can analyze these circuits in more detail. Rest two circuits are remained for this particular question. I'll talk in the coming part. So this is enough for this. If you have some doubt remain that you can see or you can analyze the circuits again, you can post me the doubt. But try to remember the concept of two current sources in series is very important. Okay. So I think I have cleared whatever possibly I can clear the doubts of the people for this particular question. And you can use these things and whatever the takeaways you can take from here, you can use for your placements. I think a lot of things are discussed here. So these all four circuits I explained what I could. If you have some more viewpoints, you can share on our Telegram group. And for more discussion, we'll carry in some other part or next part. So thank you for this part. Okay.